I was working in my office, as I often do, when my friend lobbed a question into the group chat. Being the sole bearer of the math torch, I had to give it an honest shot. Here's what he said. Here's a probability distribution. I know that the expectation E x equal to A is P times A. But what about the variance? Is that undefined? I was like, yeah, cool. Wait, what? What do you mean by the expectation of a value? You can only have an expectation of a distribution. So the first thing I did was to rephrase this in terms of distributions so that it would make a little bit more sense. If you only want to care about a single value A, then we can make a distribution with only that value appearing while the rest of the values go to 0. Given a distribution X where A appears with probability P, we define X sub A to be a new distribution where A appears with probability P and 0 appears with probability 1 minus P. If we find the expectation of this distribution, which we can do by summing out the probabilities times values, it comes out to be P times A, exactly as my friend wanted. This distribution basically asks how much does a value contribute to the value A. Well, A contributes the value A itself with the probability P, and everything else contributes 0 to it. Once you have this distribution in hand, we can use this formula to find its variance. After an algebraic dance, we see that the variance is A squared times P times 1 minus P. It wasn't until I had reached home that a bolt from the mathematical sky struck me, inciting insight and embarrassment in a single stroke. This distribution is just a weighted Bernoulli trial. A p-Bernoulli trial is a distribution for a weighted coin where 1 appears with probability p and 0 appears with probability 1 minus p. In our case, we scale the 1 by the value a. Let us go back to the probability table. What motivated my friend to ask this question is that the expectation can be computed like this. Each term in this expectation is the expectation of each value in some sense. This can be rephrased pretty nicely now. We break up our probability distribution as a linear combination of these Bernoulli trials. The expectation of a Bernoulli trial is P, and by linearity, we see that the expectations on the right side add up to give the one on the left. So they do indeed match up. The variance, as we saw, is a squared times p times 1 minus p, which is just a squared times the variance of a p-Bernoulli trial. The expectation is linear, but how do the variances add up? I didn't know this, so my friend told me that if you have two distributions a and b, then their variance is given by variance of a plus variance of b plus 2 times the covariance of a and b. That equation looks super suspicious, right? If you squint really hard, you'll see it. No, not the fly. I need to close my windows, man. If you look at the equation, it looks like taking the magnitude of a vector, which you might have seen written like this. The covariance acts like an inner product, like a dot product. And in the background, that is kind of what's happening, I guess. The Bernoulli trials form a basis for the set of discrete probability distributions, and so we project the distribution onto each basis element. And when we want to put it back together, we need to use the inner product if the bases aren't orthogonal. So, what is the covariance of our distributions? We can compute covariance of A and B using the formula expectation of product minus the product of expectations. If x sub A takes the value A, then any x sub B has to take the value 0. Because if A appears in our trial, then nothing else can appear in that trial. Two values cannot happen simultaneously. So the product xa times xb, when A is not equal to B, is always 0, and so is its expectation. This leaves us with the covariance being negative of A times B times the probability of A times the probability of B. Now that we have all of our mystical ingredients, we can put them into the cauldron of the variance formula and start up a proof. In a basic probability class, we learned that the variance of a distribution can be written as a sum of probabilities times value squared minus the square of the expectation of the distribution. So we get this on the left hand side. We will denote by capital A the finite set of values that x can take. Now we use our variance of the sum of distributions formula on the linear combination, for which we need its more general form, which you might have seen in the case of vectors. We get the first term as a sum over values in A of a squared times p times 1 minus p, and the covariance part, which is the sum over pairs a comma b where a and b are both in A and A is not equal to B. And this term is the same one we have seen before, which is negative of A times B times the probability of A times the probability of B. Expanding the first term, we get this. And we notice that this negative times A squared times the probability of A squared can sneak out from the first sum into the second sum. If A were to be equal to B here, then this is exactly the term we would get. And hey, good for that term, it's found its people. This sum now becomes over all A comma B, where both A and B are in capital A. This can now be rewritten as a square of the sum over all elements of A. And what do you know? If you squint hard, okay, not that hard, you'll hurt yourself. If you squint moderately, you will see that this is exactly the term on the left. So this works. The moral of the story is that you can break up a finite distribution into a linear combination of Bernoulli distribution, and this preserves the information about the mean and the variance. Well, thanks for watching. So the important question that my friend was really asking was this. You see that the contribution of Bernoulli trial makes to the expectation was A times B. And the contribution to the variance by each basis element is, I think, the sum of covariances like this. There's another formula for variance. Is there a vector-like interpretation for the summands of this formula? And what more can be done with this interpretation? I'm not a probabilist, so this probably appears in the literature somewhere, and I just don't know about this. Do you know what it's called? If yes, please let me know in the comments. That's all I had. Bye for real this time. Thanks for sticking around.